Magnetic force on moving charges. So we're going to try to do a little experiment here. If I take a wire, any wire, and I put a compass next to it, well, normally the compass just aligns itself with magnetic north, so it points towards north. Now, if I hook up that wire to a power source like a battery, or I plug it into the wall, what happens is my compass turns. If I unplug it or turn the power off, my compass goes back and aligns itself with the magnetic field of the Earth. It's kind of a neat experience. So turn the power back on, and all of a sudden, something's causing the compass needle to move. Well, the only thing that will cause a compass needle to move is another magnetic field. So it leads us to conclude that when you have a current running through a wire, it produces a magnetic field around it. So let's read a little more. It says, if you place a compass needle next to a conducting wire with a current running through it, the compass needle moves. This demonstrates that the current in the conductor produces a magnetic field, which interacts with the magnetic field of the compass needle. And we can conclude something from that. So therefore, a current can exert a force on a magnet, and that a magnetic field can exert a force on a current, or moving charges, because all current electricity is moving electrons. If you wanted to calculate the magnetic force, so we use capital F and M for magnetic, so magnetic force, the formula is QVB sine theta. So Fm is the magnitude of the force on the moving charged particles. Q is the amount of charge on the moving particle. V is the velocity of the moving particle. And B is a new symbol. We haven't seen that before. It's the magnitude. So that's how big the magnetic field strength is. And B is measured in this unit called Teslas, and we use the symbol capital T. Now, it depends on our wire. Like if our wire is going into the magnetic field perpendicular, that means sine theta is 90. And if they don't indicate an angle, that means it's going in on an angle. We're always going to assume it's 90. So that's important. So if no angle is given, assume that theta is 90 degrees. An electron accelerates from rest in the horizontally directed electric field through a potential difference of 46 volts. The electron then leaves the electric field, entering a magnetic field of magnitude 0.2 teslas directed into the page. And it says to calculate the initial speed of the electron upon entering the magnetic field. So first thing I want to do is write down my given information. So I know in the question it tells me the voltage is 46 volts. The magnetic field, the symbol for that is capital B, is 0.2 teslas. I'm looking for the speed. So these two V's are not the same. So I like to draw voltage as a capital V and then speed as a kind of like a smaller V with a little tick on it. And then I get these two values from page 710. So there's a table on page 710 and it gives us some constants. And I'm specifically looking for the mass of an electron and the charge on an electron, because it's an electron that we're accelerating. So once I have all my given information, I need to think about my question again. So I start from rest, and then all of a sudden I go through this electric field. So I have electrical energy. And then when I leave the electric field to enter the magnetic field, well, I have speed. So all that electrical energy got changed into kinetic energy. Now, let's think about my formulas with electrical energy. I know that the definition of voltage, electrical potential energy, is equal to how much energy per unit charge. So if I rearrange this formula for EE, I get EE is equal to QV. So I'm going to substitute that in. So up here, I'm just going to write down Q, capital V, because that's voltage, is equal to my formula for kinetic energy, which is 1/2 mv squared. And I'm trying to solve for little v. So to do that, to get rid of the half, I'm going to multiply it by 2. To get rid of the m, I'm going to divide by m. And then I'm going to take the square root of both sides. So when I do all that, I end up with the square root of 2q capital V over m. Now what I want to do is just plug in everything I know. It's going to be a big square root. So 2 times the charge on an electron, which is 1.602 times 10 negative 19, times the voltage, which I know is 46, all divided by the mass of an electron, which is 9.11 times 10 to the negative 31. When I put all that into my calculator, I end up with 4.0 times 10 to the 6 meters per second. So what's happened is my electron, which started at rest, went through this electric field, and it sped up to 4 times 10 to the 6 meters per second. In B part, it says calculate the magnitude of the magnetic force on the electron. So it doesn't mention an angle, and whenever it doesn't mention an angle, you're always going to assume the angle to be 90 degrees. So theta is going to be equal to 90 degrees. And I'm looking for the magnetic force. So Fm is what I'm looking for. So we get to use our new formula. So our new formula was Fm is equal to QVB sine theta. And we just plug in everything we know. Because it's an electron, the charge on an electron is 1.602 times 10 negative 19. This V is our speed, and we just calculated the speed in A part. So in this formula, when you see the V there, don't get it mixed up with voltage. It actually is the speed. So that's 4 times 10 to the 6. B is our magnetic field, which is 0.2, and sine 90 degrees. And the cool thing about sine 90 degrees is it's equal to 1. So we put all that into our calculator, and we end up with 1.3 times 10 to the negative 13, and force is always measured in newtons. C part, it says, calculate the radius of the electron's circular path. So we're looking for R now. Well, the magnetic force is equal to the centripetal force because it's traveling in the circular path. And we know a formula for centripetal force, and that's mv squared over r. So if I take my magnetic force that I calculated in B part, put it over here, then all I have to do is solve for r. So r is in the denominator, that's always a problem, so I need to bring it up to the numerator, and then I'm going to bring the force down here. So they kind of switch spots. So we have r is equal to mv squared divided by Fm. Put in what you know. So mass of an electron is 9.11 times 10 negative 31 times my speed, which I calculated in A part, 4 times 10 to the 6 squared, divided by my magnetic force, which I did in B part, which was 1.3 times 10 negative 13. I get the radius, which is 1.1 times 10 to the negative 4 meters.